Okay, thanks for the invitation and introduction. It's my great pleasure to give a talk here. So my talk is about this 3D Navier-Stokes equation via this convex integration method. And my talk is based on the joint work with Martina and Xiangchan. And the reference for my talk is already on archive. Now we consider the Navier-Stokes equation on the three-dimensional torus. And in this talk, I will concentrate on this Navier-Stokes system driven by the space-time white noise. And here, this U will denote the velocity field at time t and position x. And P is the pressure term. And here, this driven noise is space-time white noise. And also satisfy this divergence-free condition. And the motivation to add in this space-time white noise comes from this study of these sigma fluctuations. In fact, this sigma fluctuations comes from appears in the on the level of molecular fluids. In fact, this has been derived by Landau and Lifshitz to study this kind of motion. So they derive motions called this Landau-Lifshitz Navier-Stokes system. And in this case, this Navier-Stokes system are driven by the divergence of the space-time white noise. But if we consider driven noise given by the divergence of space-time white noise, it's critical in 2D and supercritical in 3D. This critical and supercritical is in the sense of the regularity structures by Martin. We cannot solve it. So we just consider space-time white noise for simplicity. On the other hand, if we consider the large scale dynamics, and any 2 points in the large scale dynamics are far away from the molecular level. So in this case, the correlation should be uncorrelated. So we just consider this space-time white noise. And this kind of space-time white noise also appears can be seen from the scaling image from some vortex approximation, Eulers perturbed by some transport noise. So they do some scaling for the transport noise. So the third motivation is if we consider this space-time white noise, it just can be seen as it's like we add the Brown emotion on the every Fourier basis in L2 space. In this case, we have full noise, so we can have some regularization by noise effect. In this case, we can get the strong Feller property. And before proceeding, we just recall some results in the deterministic setting. In fact, this Navier-Stokes system has been studied a lot in the literature. Just to recall this famous work by Larray in 34, he already can prove the global existence of these weak solutions for all dimensions. And a recent breakthrough work by this Master and Wico, they could prove this non-uniqueness of analytical weak solutions. And this weak solution a little bit weaker than this Larray solutions. And more recently, there are this by this Colombo and their co-authors for this they can prove there exists some force such that the non-uniqueness of this Larray solutions hold. And in the stochastic setting, in fact, for two-dimensional cases also have been studied a lot. We just concentrate on the three-dimensional case. For the three-dimensional case, if the driven noise is so-called the trace class times noise, so that means the driven noise for time direction is like the Brown motion, the derivative of the Brown motion. For the spatial variable, it's in fact regular with respect to spatial variable. In this case, the martingale solutions have already been constructed by Flandoli and Romito. In this case, this martingale solution is like a stochastic extension for this Larray's work, this Larray solutions. And in general, if we have the uniqueness, like the pathwise uniqueness of the solutions, the solution will form a macro process. It's like flow properties for the solution. But in this case, we don't have uniqueness. So they could do something called this Markov selection and find the Markov solutions also been constructed in their work. And more recently, we're using this, the convex integration method developed by this Master and Vico, we could prove, first we could prove the non-uniqueness law for the related martingale solutions. Now this martingale solutions just gives the law of the solutions such that using the law, under the law, the canonical process will satisfy the equation. And the non-uniqueness in law is a probability concept, which is stronger than this this pathwise non-uniqueness result. And we could even see the mark solutions are also not unique. And another thing we could prove from this convex integration method is we could construct directly this global probabilistic strong solution. In classical results, they only have the law of the solutions. So they need to put it on the canonic space to see the solution satisfy equation. But this probabilistic strong solution, in fact, it's like we fix the stochastic basis. And on this stochastic basis, we could construct the solutions for this given stochastic basis, and the solution is adapted to this filtration generated by the related noise. Since this convex integration method just using the iteration step, so we could always keep this adaptiveness property. So this is for the trace class noise. Today I'm going to concentrate on this Navier-Stokes system driven by this spacetime white noise. So we just recall the definition for this spacetime white noise. It's just a random Gaussian functions with the covariance given by this delta functions. So this just means for different spacetime points, it should be independent. But delta function is just a generalized function, which makes this the regularity for this psi. In fact, it's not a function, but just a distribution. So it stays in this kind of base of space. So this just this Holder space just means like this base of space with P and Q equals to infinity. Here we can see when here this space is in fact is a time space is a time and space space depending on time and space, and with parabolic scaling. And when time when the dimension becomes larger, this psi will become more rough. And the last minus just means minus kappa for any kappa bigger than 0. And here we have the regularity for the psi stays in this space. And even we have the so-called this Schauder, we have Laplacian operator, we have the Schauder estimate. We get 2 regularities. So in 2-dimensional case, we could see the U is not a function, but a distribution. And we can see, recall this result from harmonic analysis. We cannot make sense of this nonlinearity in this case. And for 2-dimensional case, we could using this so-called Duprat and Bush trick to solve this problem. In fact, we could decompose this U to the following 2 equations. They satisfy the linear part, and we satisfy the nonlinear equations. And this red terms is also not well defined in the classical sense, but it's in fact Gaussian. We could use a probabilistic approach to do like the renormalization to make sense of it. And the regularity for this way, in fact, stays in is better. And every term on the right hand side satisfies these conditions as alpha plus beta bigger than 0. So in this case, we could using the fixed point argument to obtain local solutions. And for the global solutions, in this case, if we consider the Navier-Stokes system, and we take in the inner product for the nonlinearity with the Laplacian U, it's equals to 0. So in this case, the related Gaussian free field gives the invariant Mayer. We could use in the Bagain's argument to derive the global solutions by using this invariant Mayer. And furthermore, here we have enough noise. So in fact, using this idea from this higher and Martina, we could even obtain the strong failure property. This also gives the global solutions from every starting point. However, this trick breaks down for the three-dimensional case. If for three-dimensional case, they is even more rough. And if we iterate this trick again to do further decomposition, in fact, this red term always, there's some problem to make sense of this red term due to the properties for the regularity. And here for this red term, it contains this non-linearity, so we cannot do for even we do further decomposition, we cannot handle it. To solve this problem, we need to use the theory of these regularity structures by Heil, or using this paracontrolled distribution method by Gubinelli, Keller, and Tarkovsky. This could help us to get the local opposeness of this kind of model, three-dimensional case. However, now if we only have the local solution, recall we just mentioned in the for the deterministic Navier-Stokes system, we have the global solutions. This is global weak solutions by Leray. So our problem is whether we could derive the global solutions by using PDE argument. How can we derive these global solutions by using some uniform estimate? This kind of problem has been studied a lot in the field of singular SPD. There are two classical examples. The first one is this so-called dynamic 5-4 model. And for these models, there's the nonlinearity. We will have the -5 cubic term. This gives us some dissipation effect from this nonlinearity. So due to these terms, the first work for these global solutions in the field of singular SPD due to this Morant and Weber, they could derive the global solution, global opposeness for the 5-4-2 and 5-4-3 model. And later has been extended by Gubinelli and Hofmanova to the whole space. And also another important model is called this KPZ equation. And one is using the so-called Kohoff transform to study this, to transform it to a linear equation. And another way is our recent work, we could using something called, we could using the maximum principle and also Spoken transform to do some some KPZ type equation. However, the ball trick does not be applied to this Navier-Stokes system driven by space-time white noise. Reason is here we don't have the strong drift term like this -5 cubic term, and we can also not using the maximum principle and also this so-called this Kohoff transform. For the two-dimensional case, the existence of the invariant, we use the invariant Mayer and Bogus's argument to get the global solution. However, the trick breaks down for 3D. We don't have such kind of invariant Mayer in this case. And another trick is for the deterministic Navier-Stokes system, the L2 energy estimate is very useful to derive the global solutions. But however, in this Navier-Stokes system, driven by space-time white noise, we could not use this trick. In fact, we tried this problem for 2D case for a long time, but we didn't succeed. In fact, there's due to the singularity of this coefficient, there will be some non-linearity appear if we want to using this energy estimate. And for 3D, it looks hopeless to direct using the energy estimate. And our main result is if we consider the given initial value in L2 space or in this kind of basal space, then we can obtain there exists infinite many global solutions, also probabilistic strong solutions for this Navier-Stokes system. And the nonlinearity here, we also need to make sense of it by using this paracontrolled distribution method. And here I just give some idea of the proof for this kind of a result. To obtain the uniform estimate, first we also need to decompose our equations to some regular part and irregular part. For the in general, for this, we want to apply this convex integration method, but this method only works for the coefficient should be function valued. So we just do this decomposition. And we want to using the convex integration for the regular part, and using the Schauder estimate and the paracontrolled calculus for this irregular part. And our decomposition are based on this Bernoulli pair product and using some localizers here. And so here, as I mentioned, we just using this paracontrolled calculus for irregular part, then we could make sense of this irregular part. And for the regular part, we're using this convex integration method.
Rongchan?
Okay, so in this case, the idea for the proof, in fact, is we put the irregular part using this paracontrolled calculus and the Schauder estimate. And for the regular part, we're using this convex integration method. So in fact, our decomposition, we put the linear part to this irregular part, and also put all this non-linearity still in this regular part. And for the regular part, we're still using this scheme for convex integration, like the iteration. And here, using this cancellation for this non-linearity. And this is also comes from this building block of using it from this Buckmaster and Vico, this intermittent states. And this gives us the existence of this probabilistic strong solutions and also this analytical weak solutions. And the solution, in fact, will first exist beyond some stopping time or before some stopping time. And here we just using the stopping time to control the noise uniform in omega. So this stopping time only need to control the noise and also the renormalized terms. And the related energy is close to a given constant K. So this gives us infinite many solutions. And finally, we just connect solutions to infinity. This gives us a construction of the solutions. And we just consider, in fact, our method have more flexibilities compared to this environment Meyer approach. We could using this method to cover the regime from the trace class noise to this space-time white noise case. And I think this also we could do even more rough noise. And this is our main results. And I was asked to propose some problems. And I think our approach could be used to other models, especially the models from the fluid dynamics, which have been successfully used by using this convex integration method. And now I just want to talk other problems from this singular SPD. One of the main motivation to study the singular SPD is in so-called stochastic compensation. Maybe just go to next slide. So now we consider the stochastic compensation of this Yang-Mills field. And in this case, we just consider this in fact, the stochastic compensation just means we consider a quantum field, and the stochastic compensation just means we find a stochastic process. In fact, is a solution to an SPD, such that it leaves this Yang-Mills Meyer and then invariant Meyer. And in this case, this Yang-Mills Meyer, this A just starts from the domain is in TD and taking values in some Lie algebra. We could, for example, consider it as some skew symmetric matrix, and this Yang-Mills Meyer, here this bracket is this Lie bracket, and we can see this nonlinearity in fact have similar singularity as this Navier-Stokes system, and the driven noise is also the space-time white noise. And recently, this and also is not well defined in the classical sense, we need to use the regularized structure and also renormalizations. And recently, the solutions has been constructed in this recent work by Heil and the co-authors. And their solution is, however, is only local. And this equation formulates will leave this Mayer and then evaluate Mayer. So our problem is whether we could obtain the global solutions in this case. In fact, this kind of space-time white noise, due to using the renormalization, it destroys the original structure of the equations. If we, without the noise in the deterministic case, this kind of model just gives by the gradient flow. So using the gradient flow and also the local opposeness result, the global solution could be constructed. However, in this case, there are a lot of terms need to do renormalization. We don't know whether this convex integration method could be used for this kind of model to obtain the global solutions or even the global stationary solutions. And maybe this gives PDE constructions to this Yang-Mills field. In fact, this stochastic compensation has been used successfully for the study of the 5,4D field. For this work, and in fact, for this kind of SPDE, as I just mentioned, due to the minus 5 cubic term, this gives us this dissipation, so we can get the uniform estimate and give a PDE construction to this 5,4,3 field. This is our problem. We have tried some simple models for this Yang-Mills stochastic compensation of this Yang-Mills field, but since the intermittent jets for the Navier-Stokes system does not work in this case, so we don't know whether it's possible to construct other building block to give global solutions in this case. And another problem we want to understanding also related to the singular SPDE is also related to our recent work on this surface quasi-geostrophic equation. We consider perturbed by some just special perturbations. And in this case, this kind of model, if we understanding using the theory of these regularized structures, it's just since this gamma can change from 0 to 3/2, it covers from this critical and supercritical case. So in this case, this kind of the critical means if we calculate the regularity for the nonlinearity, in fact, this regularity have the same regularity as the noise part, and here the noise is also very rough. In this case, we could using the this convex integration method to construct the global solutions and or even global stationary non-Gaussian global stationary solutions by this convex integration method. And so our problem question is first, here our driven noise is just some special perturbations. And we don't know whether we could cover some rough noise, like this space-time white noise. And using this convex integration method to understanding the single SPD in the critical and supercritical case. An example for this case, we just leave it like here. So here's my talk. Thank you for your attention. Very sorry for this internet problem.
And good job powering through the technical difficulties. We have time for a question or a comment.
So I just have, do you think you could maybe comment a little bit on what the technical difficulties are with putting the space-time white noise under the divergence for 3D Navier-Stokes?
You mean the divergence, or add the divergence to the critical? For 2D, maybe we just go back to the first slides. Maybe I just explain. If we calculate the regularity of the, maybe I just go back to the first slide. So,
Yeah, just go back.
just the first slide. If we calculate the regularity, I don't know whether I cannot see it. Just if we as for the space-time white noise, if we remember the regularity, it's just the same -1 minus the d/2 minus. So if for three-dimensional case, it's just given by the C minus. It's in three-dimensional case, it's given by C minus 3/2 minus.
Five
Sorry.
half.
C minus 5/2 minus. And if we take the divergence, so we lose one regularity. So we get C minus 7 minus 7/2 minus. And using the shorter estimate, we calculate the regularity. In fact, we will see the non-linearity. In this case, if we put 3D, here the solution will be in C minus 3/2 minus, and the gradient will also lose one regularity. So in fact, you could calculate easily. This part will have worse regularity compared to this side. So this means the supercritical. If you calculate for the 2D case, the regularity for the divergence of the psi is just equals to the regularity for this non-linearity. So this means critical. And if we're using the regularity structure theory, we will do such kind of expansion. Formally, we will meet infinite many terms need to be renormalized. But in Hall's regular structure theory, can calculate consider the subcritical case. So the subcritical means the renormalized term are only finite terms need to do can be renormalized. When we're using this, convex integration method, and we find in this case, when we use it, it seems the solution is when we construct the solution, we could using the building block from this convex integration method. And this kind of building block, for example, for this quasi case, this building block is the fully support of this fully frequencies. In fact, is stays in the analysis, which is far away from the solution. For example, if we come from this UQ to this UQ plus 1. So this we will, for some term, we will not meet the well-defined problem in this case. So I think maybe this convex integration method could help us to understanding this critical or this supercritical case.
Okay, thanks, Rongchan. Thanks for the question. Let's thank our speaker one more time.